So take a look at the glass of ice water sitting on your desk right now. Or if you're driving, picture a foggy window on a cold morning.
Right, stuff we see literally every single day.
Exactly. They feel completely ordinary.
Yeah.
But here's the thing that completely broke my brain when I was digging into today's sources.
Oh, I know where you're going with this.
It's crazy, right?
Yeah.
The exact same invisible forces that are making the ice in your glass melt or, pulling that fog out of the winter air. They are currently tearing apart the crushing, chaotic atmospheres of gas giants in deep space.
It's the exact same physics.
Today, we are basically hacking the control board of the universe. We are taking a deep dive into the fundamental physics of matter, and we're going to figure out how manipulating phase transitions allows us to do things that sound completely impossible.
Yeah, because we get entirely too comfortable with the everyday behavior of matter. Like we see a puddle evaporate and we don't even think twice about it.
Not at all.
But when you look closely at what is actually happening on a molecular level, you are witnessing this incredibly delicate, violent balance of thermodynamics.
Violent is definitely the right word for it.
Right. And when we learn to isolate and manipulate those thermal levers, we step into a realm where we can preserve life-saving vaccines for years in a desert without refrigeration,
Which is huge.
or even ignite localized miniature suns in a kitchen microwave.
Okay, which massive disclaimer right at the top for you
Yeah.
listening. Do not put grapes in your microwave.
Seriously, don't do it.
We will explain exactly why it creates a literal fireball later, but do not try it at home. It will destroy your appliance and potentially start a fire.
Yeah, safety warnings aside, we do have an incredible stack of sources to guide us through all this today.
We really do. We are pulling from fundamental chemistry texts, so materials from ChemTeam and LibreText, just to ground us in the basic mechanics of the physics.
Which we need because it gets complicated fast.
For sure. We're also digging into scientific reviews on lyophilization from Medvix. We've got cutting-edge research on phase change materials from Purdue University.
The Purdue paper is fascinating.
It's so good. And we are breaking down papers on extreme fluid dynamics and that famous microwave grape plasma phenomenon from the proceedings of the National Academy of Sciences, Physics World, and the Department of Energy.
So it's a massive stack of research, right? Spanning from rudimentary high school chemistry all the way to advanced nanophotonics.
Yeah, it's a wild ride.
But there is a really clear thread binding it all together. It's the story of how matter behaves when pushed to absolute extremes and how human engineering has basically learned to ride the shockwaves of those transitions.
Let's start with the control board itself then, because to understand the weird stuff, the extreme anomalies, we first have to look at the baseline.
Solid, liquid, and gas.
Exactly. These are the three states we interact with constantly. And moving between them means we are dealing with 6 specific phase transitions.
Categorizing them by energy flow is probably the easiest way to conceptualize this. A transition either demands an input of energy or it forcibly releases energy into its environment.
Right. So like adding heat versus taking heat away.
Basically, yeah. If you want a system to go from a highly ordered state to a less ordered, chaotic state, like melting a solid ice cube into a puddle of water or boiling that water into vapor, you have to pump thermal energy into the system.
You're forcing it in.
Right. You are force-feeding kinetic energy to those molecules until they vibrate violently enough to just shatter the intermolecular bonds holding them in that rigid structure.
They literally shake themselves free.
Exactly.
And so the mirror image of that process requires giving up energy. Right?
Yeah, exactly. When a gas becomes a liquid through condensation or a liquid locks into a solid through freezing, the system is essentially hitting the brakes.
Okay, that makes sense.
The molecules are releasing their stored kinetic energy into the surrounding environment, and they're slowing down enough for those attractive intermolecular forces to, grab hold again.
So those are the 4 everyday transitions: melting, freezing, vaporization, and condensation. But the architecture of matter actually includes 2 distinct shortcuts.
Yes. Shortcuts that allow a substance to completely bypass the liquid phase entirely.
Which is so weird to think about.
It is. So sublimation occurs when a solid absorbs energy so rapidly and under the right environmental conditions that it violently bursts directly into a gas.
Skipping the puddle phase entirely.
Exactly. And deposition is the inverse of that. A gas crashes directly into a crystalline solid state.
Okay, wait, give me a real-world example of deposition.
Well, when you wake up on a freezing morning and you see frost crystallized on your windshield, you are looking at deposition.
Oh, really? It didn't condense first?
Nope. The water vapor in the air didn't condense into liquid dew and then freeze. It slammed straight from a gas into a solid matrix on the glass.
That's incredibly cool. Okay, so we have these 6 paths, right? These destinations. But what is the actual engine driving the car? The sources keep pointing back to this one thing, the ideal gas law.
Oh, the classic.
Yeah. And for anyone listening who hasn't stared at a chemistry whiteboard in a decade, it's written as PV equals nRT.
The bane of high school chemistry students everywhere.
Right. But break down what those letters actually represent in the physical space around us. Let's make it tangible.
Sure. The ideal gas law is basically the master equation for understanding how a gas behaves. It demonstrates that the macroscopic properties of any gas are inextricably bound to one another.
Okay, so let's take the first 3.
Right, so P is pressure, which is the physical force the gas exerts on the walls of its container. V is volume, which is just the amount of three-dimensional space it occupies.
Makes sense.
And T is temperature, representing the average kinetic energy, basically how fast the molecules are moving around.
Okay, I follow pressure, volume, and temperature. I can picture those. But what are the N and the R doing in the middle of all that?
Right, so the N represents the number of moles.
Which is just a counting thing, right?
Exactly. A mole is simply a chemist's way of counting microscopic things in macroscopic batches. Just like a dozen means 12, a mole means roughly 6.022 times 10 to the 23rd particles.
Which is a massive number.
Huge. But it just tells us exactly how much physical stuff is in the container. And then the R is the universal gas constant.
Okay, what does a constant do?
You can think of R as the universal translator. It's a fixed number that reconciles the mathematical units of energy, temperature, and volume so that the two sides of the equation can actually speak to each other.
Got it. So the math actually works out.
Right. And in most sealed physical systems we look at, the amount of stuff the N and the translator the R never change.
Which means the only things that can change are pressure, volume, and temperature.
Precisely.
I like to picture this as an audio mixing board for the universe. Imagine you have a locked steel box full of air. You reach over to your mixing board and you grab the temperature slider and you just push it all the way up.
Right, you're injecting thermal energy.
Exactly. The air molecules inside start dancing frantically, moving at incredible speeds. They're ricocheting off the steel walls. But because the box is locked, meaning the volume slider is jammed in place and cannot expand, the force of all those microscopic collisions just skyrockets.
Because they have nowhere else to go.
Right. So the pressure dial basically automatically dials itself up to maximum just to maintain the mathematical balance of the universe.
That's a great way to visualize it. And pushing the pressure dial up manually creates an equally intense reaction.
Oh, how so?
Well, if you take that same box of gas and you crush it down to half its size, essentially forcing those wildly moving molecules into a tiny claustrophobic space, they collide with each other in the walls far more frequently.
Because the room is smaller.
Exactly. You are doing physical work on the system by compressing it. That mechanical work translates directly into heat. So the temperature dial spikes simply because you force the volume down and the pressure up.
That is wild. Those are the invisible knobs dictating the state of all matter.
They really are.
And to really grasp the sheer violent magnitude of the forces we are talking about when those dials move, we have to talk about the 55-gallon drum experiment.
Oh, this is a classic.
The texts describe this as a classic, but honestly somewhat terrifying chemistry demonstration.
It's definitely dramatic.
Right. So picture a massive, heavy-duty steel drum, the kind you see on industrial shipping docks. A professor puts a few inches of liquid water into the bottom, leaves the top cap completely unscrewed, and places a massive industrial burner right underneath it.
Just blasting it with heat.
Yeah, he boils the water until a thick, heavy pillar of steam is roaring out of the opening at the top.
So at that specific moment, the liquid water has absorbed massive amounts of thermal energy, vaporized and expanded.
Right.
As it turns to steam, it physically pushes the normal room air out of the top of the drum.
Because the steam needs the space.
Exactly. The entire interior of that 55-gallon steel cylinder is now occupied almost entirely by superheated gaseous H2O.
And this is where the trap is set. The professor takes a heavy wrench and tightly screws the cap onto the drum, completely sealing it.
Locking the system.
Yes, it is now a closed thermodynamic system. He turns off the burner, he slides the drum to the side of the lecture hall, and just starts teaching his class.
Just ignores it.
Just completely ignores it. The drum is sitting there in ambient room temperature, So the temperature dial on our mixing board is slowly, passively sliding downward as the steel radiates heat into the room.
Right. And following the ideal gas law, as the temperature drops, the kinetic energy of the steam drops.
The molecules slow down.
Yep. Because the steel drum is rigid, the volume is fixed. Therefore, as temperature goes down, the internal pressure must also proportionately drop.
But, and this is the crazy part, it doesn't just slowly depressurize into a cool vacuum because it eventually hits a wall.
It crosses a line of phase equilibrium.
Yes. In a fraction of a second, all of that steam undergoes a massive instantaneous transition. It condenses from a gas back into a small puddle of liquid water.
All at once.
All at once. And the moment that phase change happens, the heavy steel drum violently implodes. It crumples in on itself with a deafening bang, basically flattening like someone stepped on a thin aluminum soda can.
It's shocking to watch.
It is. Yeah. How does simply changing from steam to water unleash that much destructive mechanical force?
Well, the violence comes from the staggering difference in volume between a gas and a liquid.
Okay, explain that.
Remember the N in our equation, right? The number of moles. One single mole of liquid water takes up about 18 milliliters of physical space.
Which is tiny. You could swallow it in one gulp.
Exactly. But 1 mole of water vapor at standard temperature and pressure occupies over 22 liters of space.
Wow, wait, so it expands by a factor of...
Over 1,000.
That's insane.
So when that drum cools and crosses the condensation threshold, the gas essentially vanishes from the perspective of the volume it occupies. It collapses into a tiny puddle at the bottom.
Creating a massive void.
Right. The internal pressure instantly plummets to near absolute zero.
But the drum isn't pulling itself inward, though, is it? It's the atmosphere outside the drum doing the trushing.
Exactly. And this is something we completely ignore because human bodies evolved to push back against it seamlessly.
We don't even feel it.
We don't. But the weight of the miles of air above our heads is constantly pushing down on every square inch of surface area at roughly 14.7 pounds of force.
So normally the air inside an empty drum pushes outward with that exact same 14.7 pounds of force, achieving equilibrium.
Yes, but when the steam in the drum condenses and the internal pressure drops to near zero, you suddenly have tens of thousands of pounds of atmospheric force pressing on the outside of the steel.
With absolutely nothing pushing back from the inside.
Nothing at all. The structural integrity of the heavy steel yields instantly. It is just a visceral visualization of how much invisible energy is suspended in the phase state of a material.
It's terrifying. So if manipulating temperature and pressure can crush an industrial steel drum in a blink of an eye, we need to know where the guardrails are. We need a map so we aren't just turning these knobs blindly.
Which brings us to phase diagrams.
Yes. I look at a phase diagram like a territorial map of a substance. You have temperature running along the bottom axis, right? And you have pressure running up the vertical axis.
Right.
The map is basically carved into 3 main territories: solid, liquid, and gas.
And the borders between those territories are the lines of equilibrium.
What happens on the border?
Well, if your specific combination of temperature and pressure lands you exactly on one of those border lines, it means the substance is existing in 2 physical states simultaneously, in perfect thermodynamic balance.
So like ice melting.
Yeah. A glass of ice water sitting perfectly at 0 degrees Celsius is resting precisely on the solid-liquid equilibrium line.
Okay, that makes sense. And if you follow all the borders to the point where they intersect, you find the X on the map, the triple point.
Ah, the triple point. It represents a single, incredibly specific coordinate of temperature and pressure where all 3 lines meet.
And what happens there?
If you can hold a substance in a chamber at that exact mathematical point, it will exist as a solid, a liquid, and a gas all at the exact same time.
All 3 at once.
Yes. You will literally see liquid boiling into vapor while simultaneously freezing into ice, while the ice sublimates back into vapor.
That sounds like a glitch in the Matrix.
It looks like one, too. It is this chaotic, beautiful state of perfect equilibrium.
But every substance has its own unique map, right?
Correct. Every
Right.
molecule behaves differently.
Because carbon dioxide, for instance, has a massive anomaly on its phase diagram that we actually experience all the time.
Right, dry ice.
Yeah. For most materials we interact with, normal Earth atmospheric pressure, 1 atm, is situated high up on the vertical axis, well above their triple point.
Right.
But for CO2, 1 atm pressure is actually situated below its triple point.
Which changes everything.
How so?
It means that under normal atmospheric conditions on Earth, liquid carbon dioxide is physically impossible. It just cannot exist.
Because we don't have enough pressure.
Exactly. If you take a block of frozen solid CO2 and leave it on your kitchen counter, the ambient heat of the room pushes the temperature dial up.
Right.
But because the pressure dial is locked at 1 atm, which is below that triple point, the coordinate moves horizontally across the map, crossing directly from the solid territory into the gas territory.
It completely bypasses the liquid phase.
Yes, that's sublimation in action.
And that is exactly why we call it dry ice. You can hold it, it will freeze your skin, it will turn into dramatic spooky fog for Halloween, but it will never ever get your hands wet.
Because there is no liquid phase to get wet with. To observe liquid carbon dioxide, you'd have to lock a piece of dry ice in a pressurized chamber and crank the pressure dial past roughly 5.1 atmospheres.
Only when you push it above that threshold does the liquid phase become accessible?
Exactly.
Okay, so dry ice is a really fun trick, but regular ice-frozen H2O actually has a structural anomaly on its phase map that fundamentally shapes the existence of life on this planet.
It is arguably the most important anomaly in science.
Let's talk about the slope.
Sure, if you examine the solid-liquid borderline for, say, 99% of the substances in the universe, it has a positive slope. It leans forward to the right.
Okay, what does that mean practically?
That tells us that as you increase the pressure on a liquid, it naturally wants to become a solid.
Because you're squeezing it together.
Right. This makes intuitive sense because solids are almost universally denser and more compact than liquids. Compressing a liquid forces the molecules closer together until they lock into a solid shape.
But water disobeys this entirely.
Completely.
Its solid-liquid line leans backward. It has a negative slope. Why?
Water's behavior is driven by the unique geometry of hydrogen bonds. An oxygen atom is bonded to 2 hydrogen atoms in a V shape.
The classic Mickey Mouse molecule.
Right. When water loses thermal energy and freezes, those molecules don't just pack tightly together like marbles in a jar, they actually arrange themselves into a very specific hexagonal crystalline lattice.
And that shape takes up more room.
Exactly. This structural framework actually requires more empty space between the molecules than when they were just, tumbling over each other as a fluid liquid.
So the solid state takes up more room than the liquid state. Ice is less dense than water?
Which is wild when you think about it.
It is. And this is why ice cubes clink against the top of your glass instead of sinking to the bottom.
Right.
And it's why a lake freezes from the surface downward, basically acting as a thermal blanket that protects all the fish and aquatic life in the liquid water below during the winter.
If ice sank, lakes would freeze from the bottom up and everything in them would die.
Wow. Okay, wait. I want to pause and explore the mechanical consequences of this backward slope for a second.
Okay, sure.
If water's equilibrium line leans to the left towards colder temperatures as pressure goes up, does that mean I can melt ice without using heat?
Yes.
Like if I have a block of ice at 5 degrees below freezing, and I leave the temperature alone, but I just smash it with massive amounts of physical pressure, does the pressure alone force it to melt?
It absolutely does. Because liquid water is the denser state, applying immense physical pressure to the expanded hexagonal lattice of ice physically breaks the structural hydrogen bonds.
You're crushing the lattice.
Right. You are mechanically forcing the molecules to collapse out of their airy crystal structure and pack densely together into a fluid. You induce melting through pressure, not heat.
Which is the underlying physics of ice skating.
It is.
I always assumed the friction of the blade moving against the ice generated heat, and that heat melted the ice.
A lot of people think that friction plays a minor role, sure, but the primary driver is pressure. Think about the physical profile of an ice skate.
It's super thin.
Exactly. An adult human's entire body weight is bearing down not on a flat shoe, but concentrated onto a blade edge that is only a few millimeters wide.
So the pressure is just astronomically high.
Right. That creates a massive spike in localized pressure directly beneath the steel. And that intense pressure forces the microscopic top layer of the solid ice to instantly collapse into liquid water.
So the skate blade is essentially creating its own custom slip and slide track out of liquid water, millimeter by millimeter, as it moves.
Yes. And the instant the blade passes and that massive pressure is lifted, the surrounding cold temperature instantly refreezes that microscopic layer of water back into solid ice.
That is amazing. It is a continuous dynamic phase transition happening in fractions of a second beneath the skater's feet.
Just constantly melting and freezing over and over.
So there was a brilliant thought experiment in the research that connected these two anomalies. What if you tried to play a hockey game, but someone had replaced the entire ice rink with a massive sheet of dry ice? solid CO2.
Oh, this is a fun one. The players would be completely immobilized
Really? Why?
because carbon dioxide has a standard forward-leaning equilibrium line. The solid state is denser than the liquid state.
Okay.
So when a hockey player steps onto a dry ice rink, the massive pressure from their skate blade doesn't melt the ice. In fact, increasing the pressure actively favors the solid state. It reinforces the solid structure of the dry ice.
So there is no microscopic liquid layer being formed at all.
None at all. Without that liquid water acting as a lubricant, the friction between the seal blade and the solid CO2 would be immense.
Like walking on concrete.
Exactly. The skate would bite into the surface like a cleat digging into dry soil. The game would grind to an absolute halt.
I just love that mental image of professional athletes stepping out onto the ice and just sticking to the floor. But let's take this concept of sublimation, this ability to skip the liquid phase entirely out of the theoretical and into the practical.
Let's do it.
Because we use this exact physical loophole for one of the most critical logistical achievements in modern medicine, lyophilization.
Commonly known as freeze drying.
Right.
Lyophilization is literally the backbone of the modern pharmaceutical and biological industries.
It's how we stabilize biologics, right?
Yes. These are massive, incredibly intricate molecules. We're talking monoclonal antibodies, recombinant proteins, vaccines, blood plasma, various peptide therapies.
Really fragile stuff.
Incredibly fragile. And in their natural active state, these molecules are suspended in an aqueous solution. Basically, they live in water.
But water is a biological ticking clock.
Oh, absolutely.
From the sources, leaving these complex drugs in a liquid state promotes hydrolysis, where the water molecules actively start cleaving and breaking the chemical bonds of the drug.
Right, they start attacking it.
It promotes oxidation. It invites microbial growth. Water is basically the reason a vial of liquid vaccine might expire in days or weeks.
Which is a nightmare for global distribution.
Right. To stop the clock, you have to get the water out. You have to dehydrate it. But the obvious, intuitive solution is just to apply heat, right?
That's what you think.
Put the vial in an oven, boil the water into steam, and let it vent away. Why doesn't that work?
Thermal degradation. It would completely destroy the medicine.
Why?
Because a monoclonal antibody isn't just a random collection of atoms. Its medical efficacy relies entirely on its three-dimensional physical shape. The protein is folded in an incredibly specific, delicate architecture. If you heat that solution to 100 degrees Celsius to boil the water, you are injecting massive amounts of kinetic energy. The protein will violently shake itself apart to natures and loses its structural integrity entirely. If you injected that resulting dry powder into a patient, it would do absolutely nothing. The active ingredient is dead.
Wow. Okay, so we have a literal hostage situation here. We have to extract the water from the vial, but if we raise the temperature, we kill the hostage.
That is a perfect way to put it.
We have to look at the phase diagram map to find a secret tunnel out. And that tunnel is sublimation.
Right.
I kept thinking of lyophilization like an elaborate bank heist.
Yeah.
You have a priceless, incredibly fragile architectural structure, the drug molecule, and it's completely surrounded by security guards, the water molecules.
Okay, I like this.
You have to teleport all the security guards out of the building simultaneously without ever opening the doors, moving the walls, or disturbing a single piece of the priceless architecture.
To pull off that heist, the engineering process has to be deeply meticulous. You don't just dump it in a vacuum. You begin with formulation.
What does that involve?
You don't just have water and the drug. You introduce specific excipients, the most critical being cryoprotectants.
Which are sugars.
Typically specialized sugars, like trehalose or sucrose. Once mixed, you initiate the freezing phase. You drop the temperature dramatically.
So everything turns to ice.
Exactly. The water molecules pull away and lock together into solid ice crystals, while the drug proteins and the sugar molecules are concentrated into the microscopic interstitial spaces between the ice.
Okay, so we have frozen the system. We are deep in the solid territory of the phase map. Now comes the trick, right?
Now we enter primary drying. The chamber holding all these vials is sealed tight. We grab the pressure dial and we yank it aggressively downward.
Yanking the pressure.
Yes. Giant vacuum pumps suck the ambient air out of the chamber, dropping the internal pressure to a deep vacuum, typically somewhere between 50 and 300 millitorr.
Which is essentially nothing.
It is a tiny, tiny fraction of normal atmospheric pressure.
So we have dragged the entire environment below the triple point of water.
Precisely. Once the pressure is that low, the shelves holding the vials begin to radiate a very slow, very gentle heat.
But wait, if they get hot, don't they melt?
No, because the pressure is below the triple point, it is physically impossible for the ice to melt into a liquid, regardless of the heat.
Oh, because liquid water can't exist at that pressure.
Exactly. Instead, the ice crystals absorb the thermal energy, the latent heat of sublimation, and they transition directly from solid ice into water vapor.
So the security guards just phase through the walls and vanish.
They really do. The vapor is continuously pulled out of the vacuum chamber and captured on an external condenser coil that is kept at extreme sub-zero temperatures, freezing it back into solid ice, completely away from the drug.
But wait, I have a question about the structure. If you remove the physical bulk of the ice that was essentially propping everything up inside the vial, why doesn't the fragile protein structure just collapse into a useless pile of dust under its own weight?
Ugh. That is the genius of the cryoprotectant sugars we added at the beginning.
The trehalose.
Right. As the water sublimates away, molecule by molecule, the trehalose sugars physically step in and take their place.
Ow.
At a microscopic level, the sugars form hydrogen bonds directly with the delicate folded protein, acting as architectural scaffolding. They lock the protein into this rigid, what we call a glassy solid matrix.
Oh, ow.
Yeah, the protein's native three-dimensional structure is perfectly preserved, just suspended in this sugar glass.
The global implications of this are staggering. You take a life-saving biologic drug that requires constant deep freeze storage and maybe has a shelf life of a week.
And through lyophilization, you transform it into a stable, dry cake sitting in a glass vial.
You can sit in a hot warehouse or the back of a truck for 2 or 3 years without degrading.
It completely severs our reliance on the cold chain. You don't need highly specialized ultra-cold freezers to transport these medicines to remote locations globally.
And when you actually need to use it.
When a clinician is ready to administer the drug, they simply inject a sterile liquid diluent into the vial. The glassy sugar matrix dissolves in seconds, the protein drops back into its active folded state, and the medication is perfectly reconstituted.
We manipulated the phase diagram to literally pause biological time.
It is one of the greatest engineering feats in medicine.
Okay, so we've just spent a lot of time talking about dropping the pressure knob to 0.
What?
Let's completely flip the experiment.
Okay.
What happens if we crank both the temperature and pressure knobs all the way to the absolute maximum?
Oh, boy.
Like we push the substance up the equilibrium line until the line just stops.
You reach the critical point.
The critical point, what is that?
So if you follow the border separating liquid and gas up the phase diagram, you are increasing pressure and increasing temperature simultaneously.
Right.
Eventually, you hit a specific coordinate where the physical distinction between a liquid and a gas just ceases to exist.
It just disappears.
Yep. If you push the substance past that critical temperature and critical pressure, you enter the realm of supercritical fluids.
It's not a liquid anymore, but it's not a gas either.
Exactly. It is a completely new state of matter where the physical definitions are entirely blurred.
Supercritical fluids sound like something from a sci-fi movie.
They basically are chimeras. They exhibit the macroscopic properties of both states simultaneously.
How does that even work?
Because they are highly pressurized, they possess the high density and the dissolving power of a liquid. But because they are highly energized, very hot, they possess the near-zero viscosity and high diffusivity of a gas.
So they can flow like a gas, but dissolve things like a liquid.
Right. They can flow through solid matter and dissolve things in ways that completely defy normal physics.
Okay, the most relatable application of this from the sources is decaffeinated coffee, which I never knew.
Oh, yeah, it's a great example.
Because decaffeination used to involve soaking beans in some pretty harsh chemical solvents, right?
Yeah, things you wouldn't necessarily want lingering on your coffee.
But now we use supercritical carbon dioxide. You take coffee beans, put them in a massive steel vessel, and pump in CO2. You crank the pressure and temperature past the critical point.
Right.
The supercritical CO2 acts like a gas, effortlessly effusing deep into the microscopic pores of the solid coffee bean. But once it's inside, it acts like a liquid solvent, binding to and dissolving the caffeine molecules.
It just pulls the caffeine right out of the bean structure.
And then once the supercritical fluid is saturated with caffeine, you extract it from the vessel and you just simply drop the pressure dial back to normal room pressure.
Right, and what happens?
The fluid instantly crosses back into the gas territory. The CO2 just evaporates harmlessly into the air, completely untainted, leaving a pile of pure extracted caffeine powder behind.
And you get coffee beans that have never touched a toxic chemical.
It's an incredible industrial tool. But this state of matter isn't just a lab creation. If we look out into the solar system, Supercritical fluids are actually the dominant state of matter in giant planetary bodies.
Oh, absolutely. Think about Jupiter.
Right. If you were to drop a probe into the atmosphere of Jupiter or Saturn, it wouldn't eventually splash down into a distinct liquid ocean, would it?
No, there's no surface to hit. As the probe fell deeper and deeper, the crushing gravity of the planet would drive the pressure up, and the internal heat of the core would drive the temperature up.
Pushing both dials.
Exactly. At a certain depth, the hydrogen and helium atmosphere breaches the critical point. The gas seamlessly thickens into a supercritical fluid.
Without ever forming a puddle.
Right. The deep interiors of these planets are just vast, churning oceans of supercritical matter.
Okay, to understand how energy moves through these bizarre oceans, the sources highlighted a phenomenon called the piston effect.
Ah, the piston effect.
Yeah, but to study it clearly, physicists had to take the experiment to the International Space Station, away from Earth's gravity. I want to unpack this because the mechanism sounds deeply counterintuitive.
It really is. So to understand the piston effect, we first have to understand convection.
Okay, let's establish the baseline.
On Earth, if you put a pot of water on a stove, the heat from the burner warms the water at the bottom, right?
Oh, right.
That hot water expands, it becomes less dense, and it physically rises to the top, while the colder, denser water sinks to the bottom.
Right, heat rises.
Exactly. This physical churning convection is how the heat distributes throughout the liquid. But in the microgravity of orbit,
There is no up or down.
right, buoyancy doesn't exist, hot fluid does not rise, convection stops completely.
So if you have a sealed container of supercritical fluid in space, and you heat one side of it, the fluid can't churn.
It can't.
And because it's supercritical, the sources say it has notoriously poor thermal diffusivity, meaning heat doesn't naturally conduct or bleed through it well at all.
Right, it's a terrible conductor.
So it seems like it should take an absolute eternity for the heat to reach the other side of the container.
That is the logical assumption. That's what physicists expected. But when they ran the experiment, the entire volume of the fluid heated up almost instantly.
Which makes no sense.
It baffled observers until they identified the piston effect.
Okay, how does it work?
Imagine that container in space. You apply a sudden, intense pulse of heat to the left wall. The thin layer of supercritical fluid touching that wall absorbs the heat.
Okay.
Because it cannot diffuse the heat, and it cannot rise away due to lack of gravity, that microscopic layer undergoes rapid, localized thermal expansion. It physically expands outward, violently pushing against the rest of the fluid in the container.
So it acts exactly like a mechanical piston firing in an engine.
Exactly. And because supercritical fluids are highly compressible, that sudden expansion sends a longitudinal density wave, which is essentially a low-frequency sound wave rippling across the entire container at the speed of sound.
Okay, wait.
As this acoustic wave travels through the highly compressible bulk fluid, it mechanically squeezes the fluid.
Wait, I have to stop you because this is where anyone listening is going to call foul.
Oh, I know.
You were saying a sound wave acts as a heater. That sounds like pure science fiction. If my coffee gets cold, I can't just lean over and yell at it to warm it back up. Sound doesn't heat things up.
In normal liquids, no, it doesn't.
Right.
But remember, this fluid is highly compressible. When you compress a gas or a supercritical fluid, you are doing physical work on the system.
Okay.
That mechanical energy is translated directly into thermal energy. This is called adiabatic heating.
Oh, like a bicycle pump.
Yes. It is the exact same reason a bicycle tire pump gets noticeably hot in your hands when you rapidly compress the air inside it.
Okay, that makes sense.
So as the acoustic wave travels from the left wall to the right wall at the speed of sound, it rapidly compresses and releases the fluid, instantly converting mechanical wave energy into thermal energy.
So the heat doesn't slowly seep across.
Mhm.
A physical shock wave blasts across the container, instantly squeezing the temperature up uniformly.
'Cause-
The mechanical energy of sound translates into an instant thermal blanket. That is crazy. It really proves that when you push matter to the extreme, it just stops playing by the rules we were used to.
It really does. It becomes a different world.
Okay, we've looked at what happens when you maximize both pressure and temperature. What if we isolate just the temperature knob?
Oh, that's my favorite part.
We leave the pressure alone, right?
Oh.
Blocks 1 mm. But we pump so much thermal energy into a normal gas that the molecular bonds simply snap.
We enter the fourth state of matter.
Plasma.
Yes. Plasma is actually the most abundant state of ordinary matter in the universe.
Really? More than gas or solid?
Oh, by far. It constitutes 99% of the visible universe. Every star, the solar wind, the auroras dancing in our atmosphere, and the core of every lightning bolt, that's all plasma.
So what exactly is it?
When you inject a catastrophic amount of energy into a gas, the kinetic energy becomes so violent that the atoms literally cannot hold on to their electrons.
They just fly off.
Yes, the negative electrons are physically ripped away from the positive atomic nuclei.
You essentially break the atom apart.
Exactly. What was once a relatively calm gas of neutral atoms becomes a chaotic ionized soup. You have heavy, positively charged ions floating alongside tiny, incredibly fast, negatively charged free electrons.
And that changes how it behaves.
Drastically. Because the gas is suddenly filled with free-flowing electrical charges, it stops acting like a gas. Plasma is highly electrically conductive, and it responds violently to electromagnetic fields.
While plasma rules the cosmos, it is notoriously difficult to create and sustain on Earth.
It takes a lot of energy.
Except, of course, for a very famous, incredibly dangerous parlor trick involving kitchen appliances.
The microwave grape.
The microwave grape. I'm going to reiterate our warning to you, the listener right now. Do not attempt this.
Do not do it.
We're going to explain the physics in detail, so you don't have to try it. Generating plasma in a residential microwave can destroy the magnetron, it can start an electrical fire, and release plasma that will literally melt the interior of your microwave and potentially cause severe burns.
It is genuinely a destructive experiment.
Leave the flaming fruit to the physicists.
Please. But the physics behind it captivated the internet for years, mostly because the accepted explanation was completely wrong.
What was the original myth?
The classic setup involves taking a grape, slicing it in half, but leaving the two halves connected by a thin, fragile strip of skin, what everyone called the skin bridge.
Right.
You place it in the microwave, turn it on, and within seconds, aggressive sparks fly from the center, and a glowing fireball of plasma just erupts upward.
And the internet consensus was that the two halves of the grape were acting as a dipole antenna, right? And the tiny skin bridge was acting as a resistor.
Yeah, the theory was it was supposedly funneling the microwave energy until it shorted out and sparked, igniting the gas.
It sounded completely plausible.
It did. But a team of physicists from Canada finally put the theory to the test and completely demolished it. They proved the skin bridge is entirely irrelevant.
You don't even need it.
No. You don't need a cut grape. You can use two perfectly whole, uncut grapes just sitting next to each other, barely touching.
Wait, really?
Yeah. You can even use two perfectly spherical hydrogel beads, which are just synthetic polymer balls saturated with 99% pure water. As long as they are spheres of water and they are touching, plasma ignites.
Okay, so if there is no skin bridge to short out, what is physically ripping the electrons off the atoms in a piece of fruit?
The physicists identified the phenomenon as Mie resonances.
Mie resonances, okay.
To understand this, we have to look at how water interacts with light. Water has a very large index of refraction for microwave radiation.
Okay, let's pause there. Index of refraction. Break that down for an ELI 5. Explain it like I'm 5.
Sure. The index of refraction is basically a measure of how much a material slows down and bends a wave of light as it passes through.
Like looking through a glass of water.
Exactly. Think about looking at a straw resting in a glass of water. The straw looks broken or bent at the water line because the water is slowing down and bending the visible light.
Okay, I can picture that.
Well, water does this exceptionally well with the 2.4 gigahertz invisible light waves generated by your microwave. When a microwave enters the grape, it hits that high refractive index and its wavelength is dramatically compressed. The wave slows down and bunches up.
The grape becomes a trap.
Exactly. The grape acts as a dielectric resonator. The microwaves enter the spherical body of the water, compress, and begin bouncing around the internal curved walls.
Like an echo chamber.
Yes. They get trapped inside, constructively interfering with each other to set up a standing wave of intense electromagnetic energy. The grape isn't just absorbing heat. It is actively catching and amplifying the electromagnetic field.
That explains one grape. But the plasma only happens when two grapes touch, right?
Right. When you bring two of these resonating spheres together so they're physically touching, their individual trapped electromagnetic fields begin to interact.
They bleed into each other.
The fields couple together.
Yeah.
And because of the spherical geometry, they channel all of that trapped, compressed, resonant energy into a single microscopic focal point, exactly where the two surfaces meet.
You are funneling the entire 1,000-watt power output of a microwave oven into a hot spot, that is. How small are we talking?
The hotspot is confined to a region that is roughly 1/100th the size of the microwave's original wavelength.
Wow.
Yeah. For a 2.4 gigahertz wave, we're talking about focusing that energy into a spot roughly 1 millimeter across.
A spot the size of a pinhead.
Literally. The electric field concentrated into that single millimeter is phenomenally intense. It is so powerful that it actually overwhelms the ionization energy of the sodium and potassium salts naturally dissolved in the grape's water.
Oh.
The electromagnetic field literally grabs the electrons orbiting those salt atoms and violently rips them away.
Creating the plasma?
The gas ionizes, a microscopic spark of plasma ignites, and it just feeds on the surrounding microwave energy to erupt into a glowing fireball.
It is localized, microscopic chaos.
It really is.
But why did a team of rigorous physicists spend months microwaving hydrogel beads? Like, what is the real-world extrapolation here beyond a viral YouTube video?
The implications for the field of nanophotonics are profound.
How so?
Well, using macroscopic object scrapes and long-wavelength light microwaves, we managed to focus energy into a sub-wavelength hotspot.
Right.
What if we scale that down? What if we use microscopic dielectric spheres and visible light, which has a wavelength of just a few hundred nanometers?
Oh, I see where you're going.
If we can replicate this exact Mie-resonance coupling effect at the nanoscale, we could focus visible light into impossibly small spots, far below what is known as the diffraction limit.
We could create optical tools that are smaller than the wavelengths of light itself.
Exactly. That would revolutionize high-resolution biological imaging, allowing us to see individual viruses or proteins with unprecedented clarity.
That's incredible.
It could lead to nanoscale chemical sensors or entirely new architectures for optical computing. We are basically learning how to manipulate the fabric of light, all inspired by a sparky piece of fruit.
That is mind-blowing. And speaking of manipulating extremes, plasma requires immense chaotic energy, but we have actually learned to tame it, haven't we?
Oh, absolutely.
We harness these extreme states for heavy-duty industrial engineering all the time.
Industrial plasma is foundational to how we build the modern world. Consider plasma cutting and welding torches.
How do those work?
You take a highly pressurized stream of gas, often just air, nitrogen, or argon, and force it through a narrow nozzle while subjecting it to a massive electrical arc.
And the arc ionizes it.
The arc ionizes the gas, instantly transforming it into a high-velocity plasma jet.
And because the gas has entered the fourth state, the temperatures are just incomprehensible. The texts note that industrial plasma torches routinely operate at up to 40,000 degrees Fahrenheit.
It's staggering.
That is hotter than the surface of the sun, and we have it mounted on robotic arms in manufacturing plants to slice through inches of thick steel plate as if it were warm butter.
We utilize that heat for plasma spraying as well.
What's plasma spray?
You generate this 40,000 degree plasma jet, and you literally inject powdered coating material directly into the stream. Things like advanced ceramics, tungsten, or specialized metal alloys.
Okay.
The plasma instantly melts the powder and fires the liquid droplets at supersonic velocities onto a target substrate. The droplets flatten and freeze instantly on impact, creating an incredibly dense, heat-resistant coating.
Where do we use that?
This is how we coat the turbine blades inside jet engines. Without plasma-sprayed thermal barrier coatings, the metal blades would simply melt in midair from the heat of the engine.
That is terrifying and amazing. But plasma doesn't always have to melt steel, right? One of the most fascinating mechanisms I read about in the sources was cold plasma.
Oh, cold plasma is brilliant.
How can plasma, which requires thousands of degrees of energy to rip atoms apart, be cold?
This comes down to the mass difference between the particles in the plasma.
Okay, break that down.
Remember, plasma is a mix of free electrons and positive ions. An ion is incredibly heavy, an electron is incredibly light.
Right.
Think of the ions as bowling balls and the electrons as ping pong balls. In cold plasma technology, we use high-frequency electrical fields that rapidly oscillate back and forth.
Okay.
The tiny featherweight ping pong balls, the electrons, are easily whipped into a frenzy by the field. They accelerate to massive speeds, holding temperatures of tens of thousands of degrees.
But the bowling balls can't keep up.
Exactly. The heavy ions and the neutral atoms are just too massive to respond quickly to the oscillating field. They barely move.
So they stay cool.
Yes. Since temperature in a gas is just average kinetic energy and the vast majority of the ions is moving sluggishly at room temperature, the overall physical temperature of the plasma plume remains cool to the touch.
That is wild.
You have hyperenergetic, microscopically hot electrons flying around inside a macroscopically cold gas.
That is brilliant. And because you have all those energetic electrons, the plasma is incredibly chemically reactive, but it won't burn anything you touch it to.
Right.
The sources mentioned using cold plasma to treat textiles, altering the surface chemistry of fabrics at the atomic level to make them waterproof or stain-resistant without melting the delicate threads.
We also use it heavily in semiconductors.
Oh, really?
Yeah, it is vital in semiconductor manufacturing. We use cold plasma to etch microscopic pathways into silicon wafers. It has the chemical bite to carve the silicon, but the physical temperature remains low enough that it doesn't melt the microchip.
Plasma engineering is all about actively forcing matter into extreme states. But I want to shift gears and look at how we can use phase transitions passively.
Okay, yeah.
Let's look at engineering systems that manage massive amounts of thermal energy without us having to plug anything in, just by letting thermodynamics do the heavy lifting. The Purdue research paper heavily focuses on phase change materials, or PCMs.
Phase change materials are fascinating. They basically utilize the concept of latent heat.
Right. Let's define that.
When we discussed the ideal gas law earlier, we talked about sensible heat-adding energy causes the temperature to rise. You can sense it.
Right. The temperature goes up.
But during a phase transition, that rule pauses. If you have a block of ice at 0 degrees Celsius and you add heat, the ice melts. But the resulting water remains at exactly 0 degrees until all the ice is gone.
It doesn't get warmer.
No. The thermal energy is not raising the temperature. It is being entirely consumed to physically break the crystalline bonds of the ice.
The temperature dial is temporarily locked while the energy is diverted to changing the physical state.
Exactly. That hidden energy requirement is the latent heat.
And how do we use that in PCMs?
Well, inorganic salt hydrates are incredibly effective phase change materials. The Purdue study looks at materials like sodium thiosulfate pentahydrate.
Okay, quite a name.
Yeah, but this specific salt has a melting point of exactly 48 degrees Celsius. When the ambient temperature hits 48 degrees, the salt begins to melt. But to achieve that phase transition, it absorbs a staggering amount of thermal energy from its environment, up to 201 kilojoules per kilogram.
It acts as an enormous thermal sink. I love the analogy of a thermal sponge.
It really is.
Think about embedding panels of these salt hydrates into the walls of an office building in a hot desert climate.
Oh, perfect application.
As the searing midday sun hits the building, the interior temperature begins to rise. But the moment the walls hit 48 degrees, the salt inside starts melting.
And what does it do?
Begins soaking up vast amounts of heat energy from the room. The room effectively stops getting hotter because all the excess solar energy is being devoured by the melting salt.
And the cycle reverses at night. The desert air cools rapidly. The temperature in the building drops below 48 degrees, and the liquid salt hydrate begins to freeze back into a solid.
Releasing the heat.
Exactly. As it freezes, it releases all of that stored latent heat back into the building. It acts as a passive radiator, providing warmth when it's cold.
You completely flatten the temperature curve of the building without turning on a single air conditioner or burning an ounce of fossil fuel.
Just letting the phase map do the work?
You simply put the right chemical matrix in the wall. And we actually interact with this passive mechanical temperature sensing all the time. One of the best, most relatable examples in the sources was the pop-up turkey timer.
I love this one. It is a flawless piece of thermodynamic engineering just sitting in your Thanksgiving dinner.
I always wondered how they worked. I thought it was like a tiny thermometer.
Not at all. The core of a pop-up timer is a small piece of specialized metal alloy, often containing bismuth or lead. Metallurgists design this specific alloy to have an extraordinarily precise melting point of exactly 165 degrees Fahrenheit.
Which is the exact temperature at which poultry is safe to eat.
Exactly. Inside the plastic casing of the timer, there is a tightly compressed mechanical spring held down by this solid chunk of metal.
Okay, so you stick it in the turkey and put it in the oven. The turkey slowly heats up.
As long as the meat is below 165 degrees, the metal remains solid and the spring is trapped.
Right.
But the instant the internal temperature crosses that exact threshold, the metal absorbs the latent heat and undergoes a phase transition into a liquid.
And melts away.
It melts, the physical restraint is removed, and the spring violently expands, popping the red plastic indicator up. It is a completely passive, highly reliable sensor triggered purely by a phase transition.
That is so simple, but so incredibly smart.
Right.
And we take that exact same principle, the absorption of extreme heat through phase change, and we scale it up to protect human life in space.
Oh, ablative shielding.
Yes. When a NASA spacecraft, like the Apollo capsules or the modern Orion capsule, returns to Earth, it hits the atmosphere at roughly 17,500 miles per hour.
That's incredibly fast.
The aerodynamic friction compresses the air in front of the capsule, generating atmospheric plasma and temperatures exceeding 5,000 degrees Fahrenheit.
To survive that kind of inferno, engineers utilize ablative heat shields. An ablative shield is fundamentally just a massive sacrificial phase change material.
Made out of what?
It is constructed from specialized phenolic resins and carbon composites. As the capsule slams into the atmosphere, the heat shield doesn't just try to insulate the astronauts.
Like a thick blanket wouldn't work.
No, it would eventually burn through. The shield actively absorbs the thermal energy and undergoes a phase change.
The solid shield physically vaporizes.
Yes. The resin absorbs the intense latent heat required to sublimate from a solid directly into a gas.
Sublimation again.
Exactly. And as the material turns to gas and blows away in the slipstream, it carries that massive thermal energy away with it, preventing the heat from ever reaching the titanium hull of the spacecraft.
So we are intentionally destroying matter through phase transitions to shed heat.
We're sacrificing the shield to save the ship.
A disposable turkey timer and a multi-billion-dollar lunar spacecraft are operating on the exact same thermodynamic principles.
It is incredible how uniform the rules of the universe are, regardless of the scale.
It really is. We have covered an immense amount of ground today.
We really have.
We trace the line from the mathematical elegance of the ideal gas law, visualizing those invisible knobs of pressure and temperature.
And we watched those forces implode, steel drums.
We explored how manipulating the phase diagram allows us to execute the biological heist of lyophilization, preserving our most vital medicines. We plunged into the oceans of Jupiter to witness the acoustic adiabatic heating of the piston effect in supercritical fluids.
Still blows my mind.
We examined the chaotic energy of plasma, the hidden danger of microwave dielectric resonators, and how we harness phase change materials to manage energy from office buildings all the way down to re-entry capsules.
The control board of the universe is vast, and the dials are incredibly sensitive.
They really are.
And, as we refine our ability to manipulate those dials, the horizon of what is possible expands dramatically. We are just now mastering extreme states for terrestrial industry.
Right, but what about the future?
Consider the long-term trajectory. As we master supercritical fluid dynamics, could we eventually deploy tailored supercritical solvents to autonomously extract and redistribute vital resources deep within the crust of other planets? Or, as we unlock nanophotonics through microresonances and precise plasma control, could we manipulate electromagnetic fields on a grand scale to synthesize entirely new elements that don't even exist in nature?
That's the ultimate goal, right?
The physics we discussed today are the foundational mechanics required if humanity ever attempts the ultimate engineering challenge, terraforming other worlds to support life. The control board is in our hands. We are just learning how to mix the track.
A thermodynamic symphony. I absolutely love it. Thank you for joining us on this deep dive. Stay curious. Keep questioning the ordinary things around you, like that glass of melting ice water or the frost on your windshield, and keep exploring the invisible, powerful mechanics of the world. We'll catch you on the next one.